Okay, so this video is working through the notes for section R7, radical expressions. Last couple lessons we were dealing with rational expressions, but these are radical expressions. And so that means we have expressions dealing with square roots or cube roots or different radical signs. All right, so some terminology. If you have some kind of radical here, we have an index, so that's sometimes referred to as the root. So up to this point you've dealt mostly with square roots, but we'll use values other than 2. So like if I said the square root of 25, of course everybody knows that's 25. We don't generally put the 2 when it's a 2. We know without it, by default, it's the index is 2. But if we do something else like cube root, now we're thinking, okay, what's the cube root of 8? Now we're looking for a number which, when we multiply by itself 3 times, we get the number 8. So square root of 25, everybody knows that's 5, but the cube root of 8, well, that's 2. All right, so you get the idea. When the index or the root is something other than 2, we have to include it. We generally do not include the 2 when it's a second root. By default, we know it's the square root. All right, so the little symbol is called a radical sign. The number underneath the radical is something called the radicand, just to get the terminology down right. Okay. Now, there's a way of converting from, we've been dealing with negative exponents in previous sections, but now we're going to deal with exponents that are fractional. And so if I have a to the 1 over n power, that fraction 1 over n is the exponent on the a, that can be written as the nth root of a. Okay, so that's kind of how we convert it. And so more generally, if I have a raised to the following fraction, m over n, then the denominator of that exponent becomes the index, and the numerator of that fraction becomes the power. So sometimes we'll want to take the root first and then raise it to the power. Sometimes we'll want to raise to the power first and then take the root of it. Just depends on the situation and which one that we do first. All right, let's look at some examples. So the cube root of 27. So we're looking for a number that when multiplied by itself 3 times gives us 27. And so I think you can think about that, and that's clearly going to be 3. All right. The fourth root. Now, the negative out in front really doesn't mean anything. I mean, it just means that our answer is going to have a negative in front of it. But now let's look at the fourth root of 10,000. And so what number times itself 4 times is going to be 10,000? So that's just going to be 10. Right? 10 times 10 times 10 times 10 is 10,000. So the fourth root of 10,000 is 10. And then our radical had a negative out in front, so our answer is just negative 10. Okay. The next one. Now we're dealing with the fifth root. So we're getting more complex here. The fifth root. What number times itself 5 times is 243. So, you probably haven't thought about these things, and so it might take you a minute to figure out. Well, you might try, okay, well, what is 2? Is, what number is it? 2 times 2 times 2 times 2, what that is not 243. So if you did maybe 3, let's try 3 times itself 5 times, and indeed that is 243. So we have a negative out in front again, and we take the fifth root. The fifth root of 243 is 3, and so the fifth root of negative 243 is negative 3. So in other words, if I take negative 3 times negative 3 times negative 3 times negative 3 times negative 3, with 5 negative 3's multiplied together, that would give us negative 243. And so the answer would be the negative of negative 3, or in this case, just a 3. Just normal positive 3. Okay, so that's kind of what we're looking at when we're doing the fifth root. The fifth root of 243 is just 3. Okay, all right. And so you should probably, thinking about, roots other than square roots, right? So, I mean, you should know what 1 squared is, and 2 squared, and 3 squared, probably all the way down to at least 10 squared. Like, you should just know all those numbers, right? Now, when we go to cubes, 1 cubed, of course, is 1. 2 cubed, that is 8. And 3 cubed, you should know that, 27. 4 cubed, 64, and 5 cubed is 125. So you should know those. Maybe even 6 cubed, we'll use that sometimes. 6 cubed, 216. So you should probably know those. And then as we go up, like the fourth, let's say. So 1 to the fourth, of course, is 4. 2 to the fourth, that's 16. Maybe 3 to the fourth, you should probably know. That's going to be 81, and so on. So knowing those is going to be helpful for doing these types of problems. Even up to the fifth. This one was to the fifth, so it'd be like a whole nother column. But knowing these are going to be helpful in being able to do this stuff quickly, because you're not going to have a calculator to do most of these. You've got to be able to sort of know these things on your own. Okay. All right, so the next one, let's use this rule to rewrite this using radicals. Oh, also one more thing. So if I take the square root of 16, of course, that's 4, but the square root of negative 16, that's not possible, right? I can't take an even root of a negative number. Here we were okay taking the fifth root of a negative number because 5 is odd. So if I was asking for an odd number, you can take a negative because 5 negatives make a negative. But there's no number multiplied by itself here that will give us negative 16. Negative 4 and negative 4 give me positive 16. Positive 4 gives me positive 16. There's no identical two numbers that I can multiply together to make a negative. So an even root of a negative number is not possible. So just kind of as a reminder there. But remember here it's okay because it's an odd root of a negative. There are 5 negative numbers, all identical, and those would result when you multiply them together to be a negative. All right, so let's look at D then. So this rewritten would be the fifth root of negative 32. And again, negative fifth root, that's okay. I think it would be best if we look at this one as doing the root first and then doing raising that to a fourth power. So 32 happens to be a perfect fifth power. 2 to the fifth power is 32. So this all just becomes negative 2 to the fourth. All right, so the fifth root of negative 32 is negative 2. And then we raise that to the fourth power. Well, we're raising it to an even power, so the negative is going to go away. So this is just 16, positive 16. Okay? In this case, the negative is not part of the number. In other words, order of operations says that we're going to have a negative square root of 121, and then we're going to square it, right? So this negative is kind of out in front. It's really negative 1 times 121 to the 3/2 power, and so we're dealing with this 121 raised to the 3/2 power, or the square root. This should be a 3. It's the square root of 121 cubed. Okay, but the negative is out in front. It's not this, which now the negative is part of it, and we wouldn't be able to do because we'd have the square root of a negative number. So it is not that. That negative is out in front. Okay, so what is the square root of 121? Well, hopefully you know that. That is negative 11. And then that 11 is being cubed. Okay. And so we have the negative out in front, and so this is going to be negative 11 cubed is 1,331. Okay. All right, so now let's go on to the problem with some negatives then. So, and we kind of, we talked about this a little bit. If I square this -2, that's positive 4, and then as a result, I take the square root of that 4, and then I have a positive 2. So, this problem doesn't, okay, so this isn't a problem with when we have numbers, but when we deal with variables, it is. So, this kind of thing is the same thing as we have down here. So we have a squared, the square root, square root of a squared. And so we think of that as a to the 2 over 2, which is a to the 1, which is a. So the square root of a squared is just equal to a. But there's a problem here. This is true if a happens to be a positive number. But what if a is negative? So let's say that a is -3. When I plug that in, the negative here goes away because I'm squaring it. So I square -3 and I get 9. I get the square root of 9, which is 3. But that's a, but that's not what I plugged in. For us, a was -3, right? So we let a be -3. Then when we're finished, what we got is the opposite. It's not equal to a. So everybody see what we're doing here? So we plug in our a value of -3, and it ends up being 3, not a, which is -3. All right, so what we have to do is in some cases, we have to put absolute values around. This is something totally new. They did not teach you this in Algebra 1, okay? It doesn't happen very often, but there are some cases, and we'll go through some examples of when this happens. So if you're taking the nth root of a to the m, this is equal to a to the m over n, but we need absolute values in certain cases. And this is really the rule that you just have to memorize. When m is even and 1 over m, so when m, what's being raised here, is even, which means if a were negative, the negative would go away. And the resulting fraction that we use from our rule up here, if that fraction ends up being a whole number that is odd, then we need absolute values around it. All right, so let's look at some examples. The square root of 36, x to the 6. So the square root of 36, that's 6. The square root of x to the 6 is just x to the 3rd. So remember, there's a 2 here, right? I mean, we don't put it, but the square root is a 2. So what we want to think about is make this into a fraction. It's 6 divided by 2, which is 3. Okay, now, does this rule follow, right? So we don't have to worry about the numbers. The numbers are what they are, but it's the variables, because the variables can take on different values, sometimes negative. So does this fall into this pattern, right? If x is negative, the negativeness goes away here, but when we raise it to the 3rd power, it doesn't go away. So this will always be positive, but this will be negative when x is negative. So in that case, we need absolute values around the x cubed, okay? Because of just the fact that if x is negative, this one will be positive, but we're raising the negative to an even power. This will always be positive. This will be negative if x is a negative. So we need absolute values around that. All right, let's go to the next one. Cube root of 125. Well, we talked up above. Cube root of 125 is 5. And then we have 6 divided by 3, so that's y to the 2nd. In this case, the variable y, if it's negative, it'll be positive here. It'll be positive here, not a problem. The resulting fraction here, 6 divided by 3, is even, so this rule does not apply. Everything's fine here. We do not need absolute values there. All right, let's go on to the next one. The 4th root of 16, a to the 4th, b to the 8th. So the 4th root is 16. Well, that's just 2, right? All right, and again, we never need absolute values around numbers. We know those are what they are. It's the variables that cause us problem. And then we have a to the 4 over 4. 4 over 4, which is just 1. And then b is to the 8 over 4, which is b to the 2. And again, I'm just using this rule up here to get those, right? Okay, and so did any of those become odd? So yes, absolutely. 4 divided by 4 is 1. That is an odd number, so we need absolute values around the a, not the b, because its exponent, the resulting fraction, which turned into a whole number 2, that one is fine. And notice too that you really only need this when you bring everything out from underneath the radical. Sometimes, like if I had the fourth root of 16, a to the let's say to the fifth, and I was doing that one, just a simpler version of that. This would be a 2. The 16 comes out as a 2. And then this 5, right, this has got to be an A comes out, right? 4 A's in here form one out in front with another A left behind. So we have the fourth root of A. In this case, if part of that variable got left behind, we will almost never, it's very, very rare, and I won't ever expect you to do it. You don't need absolute values around this. When some of it didn't come out, right? So the ratio of 5 over 4, right? We could have written this as 2 to the a of raised to the 5 over 4 power. This is not odd because it's not a whole number, so we wouldn't really call that odd. We don't write it like this. We bring the a out in front and leave 1 back behind. It's 5 divided by 4. Think of that as 1 and 1/4. The 1 is here. The 1/4 is this part of it. So you can think of that fraction as a mixed number almost. The whole part is what's out in front. The this fraction is kind of what's left behind. So we could think of this as a to the 1 over 4 if we wanted. We decided to go ahead and write it as a radical instead. Okay, so the whole point of this is I'm not going to put absolute values around this, even though it's odd here. Part of the variable got left behind, so don't ever worry about absolute values in that case. We'll practice more of those as we go on too. I know that is kind of a new rule to never talk about that in Algebra 1. Okay, some product rules. So if I have the nth root of a times the nth root of b, I can multiply the radicands together. In this case, the indexes n and n have to be the same. I cannot multiply a square root and a cube root together. That doesn't work. The index has to be the same. And then here we have the nth root of a fraction. I can simply make the nth root of the numerator and the nth root of the denominator as well. And then when we have nested roots, so the mth root of the nth root of a, we can simply just multiply the indexes together to simplify that. Okay. So let's simplify some of these things. So square root of 3 times the square root of 27. There's more than one way to do some of these. When you're multiplying, so I can just multiply those together. So I can do the square root of the product, which is 81. And of course, we want to simplify that. And so that's just 9. Okay. Here we can multiply. The indices are the same. So this will be the cube root of x. And remember, when we multiply bases, we add exponents. So that would be to the 6th. But we want to simplify that. Basically, if this number here is bigger than the index, then we can pull stuff out. So it's helpful if you want to think of that as x to the 6 over 3. So this is just x squared. Okay, and I would say probably in this case we don't really have to worry about when you're combining stuff. Don't worry about absolute values in that case. All right, because it's 2 things up here, and it's even anyway, so we wouldn't worry about it. So that's x squared would be the simplification of that. Next one, what we want to do here is sort of do the square root of 6 over the square root of 25. So using this quotient rule up here. And then we want to rationalize. We don't like radicals in the denominator, and so we want to simplify that one. And that ends up being square root of 6 over just 5. nothing else to do because we got rid of the radical downstairs. All right, similar thing here, but instead of square roots, we're dealing with the fourth root. And so we could do the fourth root of x over the fourth root of y to the fourth. Well, this simplifies, right? Fourth root of y to the fourth, that's just y. So we have the fourth root of x over just normal y, okay? And again, you know, when you have more than one thing like this, I probably wouldn't worry about absolute values. But in this case, if you think about it, you start it even, you end it odd. So yeah, we probably should have absolute values there. Again, that's not a major issue. You know, you lose minor points if you were to forget to do that. Not a major issue, though. All right, and then the last one, we're using this rule. This will simply be the 28th root of x. And of course, you could write that as x to the 1 over 28 power. You could write it as a fraction, but generally in this case, we'll probably just leave it like that. Okay? All right, so let's look at some rules for simplifying. There's 4 things that you need to be concerned about when we're asking you to simplify radicals. So the first one is the index must be made as small as possible. So I just said before, whenever the value on the exponent under a radical sign is bigger than the index, I know that there can be some that come out. Here we have 4, it's smaller than 8, so I can't pull any out. However, I can make this index smaller. So think about writing it as x to the 4 over 8, and that could just be equal to x to the 1/2. And so really we would take this and write it as the square root of x. So I've made the index from an 8 down to a 2. And you notice you can do that when 4 is a factor of this number out here. So 4 is a factor of 8. We could reduce that fraction, make it the square root of 8. Do the same thing for the 9th root of 3. Again, a to the 3 over 9 power. Well, that reduces to a to the 1/3. That's fine. Or you could write it as the 3rd root or cube root of a. All right, so you've got to make the, and you know, even though there's not this number here, the exponent is smaller than the index, so you can't pull things out from underneath the radical, but you can reduce it, and you should. So the next one is the radicand. If it's considered simplified, then it should not have any factors in it that are perfect squares, or in this case, perfect cubes. So this case, square root of 24. Hopefully you see 4 as a factor there. That can come out as a 2, so 2 square root of 6. We're assuming that you know how to simplify radicals. If not, you need to come see me and we can practice some of those more. But square roots, you should certainly be able to simplify. Now we're getting into cube roots. So what you want to think about is what perfect cube factor. That's where these come in. You need to know some of your cubes, your perfect cubes. We're looking for perfect cube factors in 32. Well, 8 is a perfect cube. So in your mind, you want to think about cube root of 8 times the cube root of 4, because you're using this product rule in reverse, right? We're taking the a, b, and breaking it into 2 separate ones. And I did that because this is a perfect cube. So the cube root of 8, that's just 2. So this simplifies down to 2 times the cube root of 4. Normally, you think about 4 turns into a 2, but not with a cube root. That would work with square roots, but not with cube roots. Okay, we're opening up this door into different indices and different roots than what maybe you're used to. All right, no fractions under the radical. So that means we could get rid of the fraction. That's easy enough. Square root of 3 over the square root of 4. But also, now that introduces another problem in step number 4. We can't have radicals in the denominator. Well, this one's nice because the square root of 4, that just, you know, that radical disappears into a 2. So the square root of 4 is 2. So that's kind of nice. And we want to do a similar thing here. We want to break that into well, first of all, reduce these sometimes. That would be helpful. So before we even get rid of the fraction, we want to reduce that to 1 over 2a cubed. All right, and so we could definitely break that up into the square root of 1, which was just 1, and then the square root of 2a cubed. And then we would want to simplify this, bring things over, but we're going to talk about that more in the next lesson. But we want to multiply. Let's go ahead and do it here. We're going to multiply by something that will make this radical go away. So we need perfect squares down there. And so I need the square root of 2, so that 2 times 2, that gives me a square root of 4, which is a normal 2. And then I have a cubed, that's underneath the radical here. So I need another a. And I'm going to do the same thing upstairs because I have to be fair. Multiply top and bottom by the same thing. So this is going to be the square root of 2a over, and then what's left? I have the square root of 4a to the 4th. So that's just going to be 2a squared. All right, so that would be considered simplified because I no longer have a radical in the denominator. Okay, and again, if you're having problems with these rationalizing, you should have done some rationalizing of square roots. So that should be not totally new to you. If you need more practice with that, make sure that you're coming and getting extra help. So now let's look at some more examples of that. So we have the square root of 4 over the square root of 3. All right, we need to rationalize that. So in this case, because it's a square root, I need to multiply by the exact same thing here so that we get on top and bottom, because I'm multiplying by 1, and I'm allowed to do that because I've just essentially multiplied by 1 in a weird form. But this, of course, this is 2. So we have 2 square roots of 3 upstairs. On the bottom, I have just a regular 3. All right, and so that was, we've rationalized the denominator because we've gotten rid of that radical downstairs. When the denominator is a binomial like this, we can, let's do it down here, we have more room. So I have 2 over 1 plus the square root of 3. If we think about multiplying by conjugates of the denominator, that's 1 minus the square root of 3 on top and bottom. Again, we're multiplying by 1 in a weird form. Now look what happens in the bottom. We get rid of that radical. We distribute the 2. We get 2 minus 2 square roots of 3 over, and then when I FOIL this, I get 1 minus 3. Okay, that 1 minus 3 is really negative 2, so we are going to simplify that with up above everything. You know, we could factor a 2 out, so we could do 1 minus the square root of 3 over negative 2, and then I could reduce those 2's. But what I would want to do then is bring that negative up. So my final answer for this will be negative 1 plus square root of 3. All right? So that's kind of how we rationalize the denominator when it's a binomial. All right, let's move on to the next page. So our next page is going to just be practicing some simplifying. So now, up to this point, most of the problems we did, the stuff underneath completely comes out, but 288 is not a perfect square, and so it would help if you know a lot of your perfect squares. So we can think of this as the square root of 144 times the square root of 2. Now, I normally don't write this. I do this step in my head, but just so you can see what's going on in my head, I picked 144 because that's the biggest perfect square factor of 288. And so that means this will be 12 square roots of 2. And remember, there's really an implied multiplication dot there. 12 square root of 2 means 12 times the square root of 2. All right, so let's go on now. Careful, this is a cube root. So I'm looking for perfect cube factors in here. So the 81 has a perfect cube factor. I got to think of 81 as 27 times 3 because 27 is a perfect cube. That's going to come out. So the 27 comes out. I have a negative 4 out in front. The cube root of 27 is 3. I bring that out. I'm going to leave a space because I'll probably have some x, some y, and some z's there. And then what's left my cube root. So of the 81, a 3 gets left behind. Let's think about the x. So really what I'm doing is I'm saying I'm dividing 6 by 3. 6 divided by 3 is 2. So that gives me an x squared out here. There's no remainder, so there's no x's left behind. Let's go to the y now. So 5 divided by 3 is 1, so that gives me y to the 1. And with a remainder of 2, so I have y squared left behind, right? So what's happening here is I have the cube root. Let's just think about the y's for a second. Y, 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 y. I have 5 y's. 3 of them will form 1 y out in front. I have 2 y's left behind. So that's kind of what's going on in my head. Sorry, that one looks so weird. That is the exponent on it. We usually don't even write it, but just to emphasize that 3 went into 5 one time with a remainder of 2. Okay, 3 goes into 4 for the z now. 3 goes into 4 once, so that's a z to the 1, and with a remainder of 1, so we have a z left behind. All right, so and then the full answer, we want to simplify this, put it together. So it's negative 12 x squared y z cube root of 3y squared z is our final answer there. All right, so that one was a little bit complicated. This one, we can think of this 25. There is no perfect fourth power here, so it kind of feels like we're done. We can't do anything with this. If we did the fourth root of 625, that's 625 is 5 to the fourth power. 25 is too small. We can't pull anything out. However, we could write this as the fourth root of 5 squared, and then think about that as 5 to the 2 over 4 power. This is 5 to the 1/2. So this is one of those examples where if you can make the index smaller, you have to. And so this is the square root of 5. But either one, you could write it as this, 5 to the 1/2, or the square root of 5. Either would be an acceptable answer here. So you do have to simplify that. It's the whole index has got to be as small as possible thing. All right, next one. Oh, I have a negative 3 out in front. I'm looking for perfect fifth power roots here. Well, let's see. 2 times 2 times 2 times 2 times 2. So 5 2's multiplied together is 32. So 32 is a perfect fifth power. You can see that that is 32 is a factor of that. So 64 is really, you could think of it as 2 to the 6th power. So it's really the fifth root of 2 to the 6th power, and then of course there's a negative 3 out in front of that thing. All right, so we can bring a 2 out in front with, we divide, right? 6 divided by 5 is 1, so we have a negative 3. 2 comes out in front with a remainder of 1, so we have a fifth root of 2 left behind. So we want to multiply this, so that is going to be negative 6, fifth root of 2. Just gotta be careful with your index so that you don't confuse it and think that it's the exponent on the 6. All right, so that is negative 6, fifth root of 2 is that one. All right, so let's go to this one. Let's go ahead and use our quotient rule. The cube root of 2 over the cube root of 9. So we got to get rid of the radical downstairs. When this was a square root, well, if this was a square root, the square root of 9 is just 3. The radical would go away and we're fine. But here it's a cube root. So we need to turn this 9 into a perfect cube. 9 is already equal to 3 squared. We really need this to be 3 cubed. So that means I'm going to multiply by the cube root of a 3. Because that's 1 3, that's 2 more 3s, that's 3 3s multiplied together, which is 27. That's a perfect cube. So we want to do, let me get this out of the way. We want to multiply, of course, the top by the same thing because we're multiplying by 1. And so what does that give us? That gives us the cube root of 6 upstairs, And then this is the cube root of 27, which is 3, and that allows us to get rid of it. So be careful. When we were dealing with square roots, we would often just multiply whatever this number is, so we have 2 of them. But in this case, we're dealing with cube roots. So we have 2 3s, 1 more 3 is needed for 3 3s, or 3 cubed. And then the cube root of 3 cubed is just 3. All right, so now let's talk about some adding. When we add things, we can add things up, but of course this is not, we can't do this, right? We cannot add the square root of a plus the square root of a does not equal the square root of a plus a. So the square root of a plus the square root of a is 2 square roots of a. It is not equal to, the square root of 2a, right? That's kind of what this would be. This is the square root of 2a, but this, the 2 is out in front. All right, so be careful with that and how they add up. We just don't add them up. So this we cannot add up because the indices are not the same. So we could not add these. So no on this. We cannot add these. Can we add these? Well, we can't because the radicands are not the same. So we could multiply them, but we could not add them. That's what we're asking here is, can we add them? And in this case, no, the radicand, this one is 2x, this is x. We cannot add those. What about 2b and 2? Also, no, we cannot add those. Again, the radicand 2b and 2 are not the same. We can't add them. Here, the radicands are the same and the indices are the same. We definitely can add that. So we have 3, we have -4. That gives us -1, 4th root of 3x. So again, we're not changing the stuff in here. It just stays. It's almost like terms where we had 3. If we'd had 3x minus 4x, right, then that would be just -1x or -x, and the same, it works the same way here. All right, so we just add up the coefficients and this gets left behind, just like we did when we were dealing with just normal x's. All right, so in order to add these, we cannot add them because the indices are different. I'm sorry, the indices are all the same. They're square roots. The radicands are not the same. So we have 20, we have 45, and we have 80. But if we simplify these, we might see that we could do something. So there's a 4 in here. It comes out as a 2. So 2 times 2, we have 4 square root of 5 left behind. 45, there's a perfect square in there of 9. That comes out in front as a 3 square root of 5 left behind. So now it's looking promising. We can add these up. 80, with some practice, you'll remember that 80 has a factor in it of 16. You probably don't know that, but with enough practice with these things, you'll remember that. So there's a 16 as a factor of 80. That comes out in front as a 4 square root of 5. So 16 times 5 is 80, and so that's why this becomes 4 square root of 5. And now notice they're all the same. So I can simply add them up. 4 plus 3 plus 4, 11 square root of 5. Again, we don't add up the 5s and make it 15. So that's the square, it's equal to, that's supposed to be an equal sign, 11 square root of 5. Okay? All right, so we couldn't add them up the way they were. We would have to simplify them. If you are having problems simplifying this, you need to come in and get practice on that. We're expecting that in algebra and also in geometry, they had you simplifying radicals. When you did in geometry, when you did Pythagorean theorem and things like that, we were dealing with radicals. So we're expecting that you know how to simplify these. If you're having problems with those 3, then it's an indication that you need to come and get some help at lunch, and we can practice some of those. Okay, this one now. Again, these are square roots. Got to be careful because sometimes we're dealing with cube roots like we are in C, but dealing with square roots here. 98. 98, that's 49 times 2. So 49 is a perfect square. It's going to come out in front. That gives me a 7 out in front. One of these x's comes out. Remember, there's an imaginary, like an implied 2 there. So 3 divided by 2 is 1. So an x comes out and 1 gets left behind. So let's see. We have still square root. We have the 2 left behind. The 49 came out, cost us 7, a 2 left behind. One of the x's got left behind. There's 3 of them. 2 of them formed, 1 out in front, 1 got left behind, and the y didn't change because it didn't have enough to come out. And so let's think about doing the same thing to this over here. We have 3x, the 32, there's a 16 in there, that can come out. So that's going to be a 4 that multiplies by my 3 and gives me a 12. So 12x, what's left when I took the 32 out of this? When I took the 16 out of that was a 2, and again, x, y. So now you can see the radicands are the same. We can simply add these up. This would be 19x square root of 2xy. Okay. All right, now the next one's a little tricky because it is cube roots. So again, we're looking for perfect cube factors here. Perfect cube factor here is 27, so that comes out as a 3. Let's see, x is going to come out with only 1, so 3 goes into 5 once, so it's 1. 3 goes into 7 twice, so I know I'm going to have a y squared out in front. Let's see what's left behind then. We have the cube root of, we got left a 3 from that 81 to 27 came out, leaving a 3 behind. X, so we brought 3 x's came out to form this one. We have an x squared left. And then when we divided 7 by 3, that was 2 with a remainder of 1. So we have y to the 1 left behind. Again, you don't need these 1s. I'm just doing that to emphasize it for you. Now let's look at the next one, 24. Well, perfect cube in there is 8. So that comes out as a 2. And then we're going to have an x. So 3 goes into 8 twice with, and we'll deal with the square root here in a second, cube root. What's left in the 24 when we took the 8 out? Well, that's a 3. The x, 8 divided by 3 is 2 with a remainder of 2. So that's x squared left. Y, we have, so we're going to look at the 4 divided by 3. 3 goes into 4 once with a remainder of 1. So we have 1 left and 1 comes out. All right, now the radicands are the same, but the things out in front are not. So these are not like terms, right? So everything, the indices have to be the same, the radicands have to be the same, and then all of these would have to be the same if we were going to combine these. So this is like saying something like 2x minus 3x squared, right? I could not combine these because the variables are not the same to the same power. So these are not the same. So really, that's all we can do with that. We can't do anything more. All right, even though the radicands and the indices are the same, the coefficients out in front, which involve some variables, those are not the same. All right, so let's look at multiplying. What happens when I multiply two binomials that have radicals? I'm just foiling when I multiply two radical expressions. So 5 times 3, that's 15. I'm foiling this. So 5 times that, that's negative 5 square roots of 2. When I multiply the inners together, that's plus 3 square root of 32. And then we multiply these together, that's negative square root of 64. Now we want to go back and simplify some of this stuff. That can't simplify, but this has a 16 in it. So that can come out as a 4. So we have 15 minus 5 square root of 2 plus, again, that was a 16. That comes out as a 4. Multiplied by the 3 gives me 12. What's left in there was the 2. All right, and then the square root of 64, well, that's a perfect square, minus 8. So we can now combine these, right? So 15 minus 8, that's equal to 7. And these are like terms because they're the same radicand to the same index. So negative 5 plus 12, that's plus 7 square root of 2. Okay, so that's the answer for this A. And now let's look at this one. This is kind of a special case. We're multiplying conjugates together. Remember when we multiply conjugates, the outer and the inner are the same but opposite. So we can save ourselves some time by not just foiling in this case. We do the first That's 11. Square root of 11 times square root of 11 is just 11. And minus square root of 5 times square root of 5, that's just 5. And so in this case, it's pretty simple. It just goes straight to 6. So what's nice is when we multiply by conjugates, the radicals go away. And we did see that on the front of this page when we did this example here. When we did it down here, we multiplied the bottoms by the conjugate. Notice what happened is the denominator did not have a radical in it. And so that's kind of what this is demonstrating as well. All right, so last 4 examples. Let's simplify these. Part of them is rationalizing the denominator. So this is the cube root of 2/3. So I can certainly do the cube root of 2 over the cube root of 3. And now I'm going to multiply. Now, if this was square roots, I would just multiply by another 3, and then that would make 9, and the square root of 9 is 3, and the radical would go away. But it isn't square roots, it's cube roots. So 3 won't work here. What I need is 3 squared, because I have 1 3 times 2 more 3's multiplied together, and so that's 3 cubed, or 27. So that's really what we want to multiply by, the cube root of 3 squared, or 9. 3 times 9 is 27. All right, and so this becomes the cube root of 9 times 2 is 18 over just a normal 3. And so that's what allowed us to get rid of the cube root. So just be careful. You're used to maybe rationalizing denominators with radicals that are square roots. But remember, we've moved on from just square roots. We also deal with cube roots and fourth roots and so forth. So here we're dealing with fourth roots. All right, they've already separated them for us. We just need to multiply by something so that this stuff are perfect fourth powers. So we have an x cubed. First of all, it's going to be the fourth root of something, right? It's got to be the fourth root. The indices have to be the same. So I have 3 x's. I need 1 more to make 4. I have 2 y's. I need to multiply by 2 more to make y to the 4th. And then, of course, I do the same thing upstairs because I'm multiplying by 1. So xy squared. Usually I skip over this step, but let me show you what's happening in the bottom then. We have the 4th root of x to the 4th, y to the, not squared, y to the 4th. And so I usually skip over this. I'm doing this in my head. I mean, the whole point was to multiply by this, but it's not a bad idea to write it this one time. On the top, what do we have? We have the 4th root of x squared y to the 5th. All right, and so on the bottom, this just becomes an x and a y. So the 4th, so one more time, what do we got? We have the 4th root of x squared y to the 5th. Oh, that's a 5, okay. And then on the bottom, just x, y, okay. So again, we want to multiply by the minimum thing. It's not generally going to be the exact same thing that's there, like we did with square roots often. In this case, we've got to figure out what's going to make the stuff underneath, the radicand in the denominator, perfect fourth powers. So we had 3, we multiplied by 1 more x. We have y squared, we multiplied by another y squared to get y to the 4th. These are both perfect fourth powers. They just become x, y. Okay. All right, let's look at this one then. For this, I think it would be best to think about the cube root of the top, which is 3, over the cube root of y to the 9th. And then same thing here, cube root of 6 over the cube root of y to the 6th. And you can see now we can simplify this number. These are both y's. I'm being a little messy there. Y and y. Both the exponents in both of these cases are bigger than this, so those can come out. So on the bottom we have y cubed, and then on the bottom here we have y squared. Upstairs we still have cube root of 3 and the cube root of 6. And then, you know, we would probably want to be able to get a common denominator. We've done this in the previous lesson. So the least common denominator would be y cubed. I need to multiply this by y over y to make this fraction y cubed on the bottom. So that is the cube root of 3 over, minus y cube root of 6, and then just over y cubed. So that is kind of the best answer here. If you stopped here, not awful, but we really want to add those, and so you just got to get a common denominator, multiply top and bottom by y. All right, last problem. So here we want to rationalize the denominator. We did one similar to this on the bottom of the front page of our notes. We want to multiply by the conjugate of the denominator. So it's 2 plus the square root of 5. It happens to be the numerator in this case. It's not always going to be it's not always going to work out that way, but we want to take the denominator multiplied by the conjugate. So this has implied parentheses, so we have to FOIL both the bottom and the top. So the top, that's easy. It's the same binomial squared, so we know how to do that. That is the first thing squared, which is 4. It's twice the product of the two, so twice the product. So 4 square root of 5, right? It's the outer and the inner. It's doubled. And then plus a 5, because square root of 5 times square root of 5 is just 5. On the bottom, the outer and the inner, the conjugate, so the outer and the inner cancel. That's going to leave us really with just 4 minus 5. Okay? And then we want to simplify everything that we can. The 4 and the 5 can combine. Sorry, that kind of looks like a 9. That's supposed to be a 4. So that's going to be 9 plus 4 square roots of 5 over a negative 1. And I think I mentioned once in class here, you cannot have a negative 1 in the denominator. Just like, you know, if this was just a normal 1, we wouldn't write that. We would just say 5. We would say 9 plus 4 square roots of 5. With a negative, it's a similar. We just want to move that negative up. So the best answer would be negative 9 minus 4 square root of 5. We don't write that fraction when we don't need to. So get rid of that by moving the negative up, distributing it into everything. And so that is your final answer. All right, this is your homework for next class. And again, come see me for help if you are confused by any of this.